Hello everybody and welcome to Calculus 12. We're going to start off just by reviewing a few things about numbers and number sets. So, if you recall, we have a few different number sets, and we use a single letter to abbreviate those number sets. So our natural numbers are the numbers you start out learning when you are in kindergarten in grade 1. These are your counting numbers, so 1, 2, 3, 4, and so on. Okay. The next number set is whole numbers. We abbreviate that with a W. And the set of whole numbers is the same as the set of natural numbers, except it includes a 0. So 0, 1, 2, 3, and the rest of your counting numbers, and so on. Okay. The next set is the integers. We start thinking about negative numbers, but we're still using only whole numbers. So the integers, you may see it in some textbooks written as I, but the more common way of writing it is Z, with those kind of two lines going down the middle. And that's what you're more likely to see in post-secondary. So we have -2, -1, and we start at negative infinity. Not really a number, but we continue infinitely in both directions. So we have, starting at any point, we're going to go all the way up in our negative numbers till we get to -2, -1, 0, 1, 2, and so on, and then we continue going in the positive direction. We have our rational numbers. Okay, that is the next sort of nested set of numbers. And we abbreviate that as Q. Okay, sometimes you will see a little line across the Q like that. So our rational numbers are any number that can be written as a ratio between two integers. So we can define these numbers as A over B, such that A and B are elements of the set of integers. Okay. The irrational numbers which you may see written as this, or the real numbers minus the rational numbers. This is because irrational numbers are actually defined simply as numbers that aren't rational, or any number that can't be written as a ratio between two integers. The numbers, the way that we would figure out what those are, so we're able to write any whole numbers as a ratio between two integers. Any fraction clearly can be written as a ratio between two integers. Any decimal that stops can be written as a ratio between two integers if it terminates. And any decimal that repeats, we're also going to find can be written as a ratio between two integers. So the numbers that you will not be able to find a way to write them as a ratio are going to be non-repeating, non-terminating, decimals. Okay? And there are two different kinds of irrational numbers we're going to see. We're going to see numbers that are like the square root of 2. These are called algebraic irrational numbers. And you're going to see numbers like pi that are called transcendental irrational numbers. And algebraic irrational numbers can be written, we can find some polynomial with integer coefficients that gives us an algebraic answer. So that's, with rational coefficients that will give us algebraic numbers. And transcendental numbers, we can't even do that. Okay? So the real numbers, okay, is the set of all rational and irrational numbers. And if you think of a number line, it's basically any point you can put on a number line, that is going to be a real number. Okay. So, well, you might come to ask the question, if we have real numbers, what does that mean about unreal numbers? Well, the real numbers themselves are contained in a larger set of numbers called the complex numbers. So our complex numbers, which would be written as C, contains real and imaginary numbers. And we won't be getting into that in this course, but just so that you know what an imaginary number is, we define the square root of -1 to be I as our kind of initial imaginary number. And from that, we generate a whole huge set of complex numbers that include various kinds of I. And the really cool thing about I is you can actually do some real physics with imaginary numbers, and that kind of thing always just blows my mind. So it's pretty incredible. Okay, so once we have our sets of numbers, and we can kind of see them a little bit better as a diagram, so we have our natural numbers. They are in the middle. And then our whole numbers contain the natural numbers. So all natural numbers are also whole numbers. And then we have our integers, which contains our whole numbers. Then we have our rational numbers, which contain our integers. And finally, on the outside, we have our real numbers. Now this diagram does not give you an indication of the relative size of these sets. When you're measuring infinite sets against infinite sets, it's a bit difficult. So you can see here we've got our Q. So this area out here, this R, is the whole big circle. And so this part right here, the part of R that is not in Q, that is not part of the rational numbers, this is our R mod Q. Okay, this is our real number set with the rationals taken out, which we're left with our irrational numbers. Okay, so in calculus classes, you're going to need to write things using in a bunch of different notations. So we need to think a little bit about how we're going to write these sets. So we will introduce or possibly review set notation. And anytime we're talking about a notation, we're just talking about a standard way of writing things. So if we have a set A, we usually give a set a name. So let's call this one A. We can write a curly bracket or a French brace and just list what we call the elements of the set. So each of these numbers here is an element of set A. And this set A is defined, it's just got some numbers that we've listed, and we would call these discrete elements, which means we can kind of separate them out and identify each one. Okay. Let's define another set over here, and we're going to define B as the set of numbers, including 3, 4, 5, and 6. Okay. So what can we do with sets? Well, we can combine them in a couple of different ways, and we can think about them interacting in these two different ways. So one of these ways is thinking about the union of sets. So A union B, we say A union B is a set that consists of all the elements in both sets. So this is elements included in either set. So it includes all the elements in A, all the elements in B, and all the elements that are in both A and B. Okay, but if it is an element that is in both sets, we only need to list it once because it is going to be an element of this larger set. We don't need to repeat elements. So we would say one or the other or both. Okay, and Another way that we can state this relationship is we can say that this is A or B. And now the mathematical or is a bit different from the way you would use the word or in conversation. So A or B means that we are talking about elements that are in either A or B or both. This is not like your mom asking you to choose between wearing the green pants or the red pants. In this case, both is a viable option. So in this case, we have A union B, and using our A and B sets from above, it is all the numbers from 1 to 6. And we only list 3 and 4 once, even though they are appearing in both sets. So now we have A intersect B. We say A intersect B in words when we see that symbol. And this consists of elements the sets have in common. So they must appear in both sets. So in this case, A intersect B, and we would say here, this would be A and B. So the mathematical and talks about elements that are in both sets at the same time. So we have A intersect B is the set of numbers just 3 and 4. Those are the only numbers that appear in both sets. We also use this symbol here, the null set. And what that means is if we have a null set, the null set is the empty set. There's nothing in it. Not 0. 0 is not part of the null set. The null set just does not have any elements. So when we say X is an element of the null set, it means X does not exist. Okay, so it's another way just to talk about things that don't actually exist. Now we're going to go on and change gears a bit and talk about a different way to write things. So we're going to look at how we are going to talk a little bit about interval notation and then go into some inequalities and writing some different kinds of rational numbers as fractions. So, interval notation. Some of you may have seen this before, some of you may not. We have right here a number line. We are going to put a circle around 5 and we are going to draw in here. So the diagram I've drawn represents all of the integers from all of the real numbers from 0 to 5, not including 5, but including 0. So if I was going to write this using greater than, less than, equal to signs, I would write this as X is greater than or equal to 0 and less than 5. And that X is an element of the real number, so it can be anything. Another way we could write it is using set notation. So we can use our curly brackets. So we have X is a real number such that X is greater than or equal to 0 and X is less than 5. We're using and in this mathematical sense. It must be greater than or equal to 0 and it also must be less than 5. So it's all the numbers that have both. A simpler way to do this, and much shorter, is to write it when you're trying to talk about an interval within the real numbers. We have a special notation for writing those. So we would write that X is an element of 0, 5. So when we're writing the element, we know that this isn't a coordinate point we're talking about an interval. Okay? When we have a square bracket right here, this means include. And when we have a round bracket right here, this would mean that we don't include the endpoint. Okay. So now we're going to use this interval notation to solve a few inequalities. So let's look at a couple of examples. And for today, we're just going to deal with linear inequalities. So we have example 1. Let's solve 1/3 times 12 minus x is less than 2. So if I multiply both sides of my equation by 3, I get 12 minus x is less than 6. If I add x to both sides, I get 12, not 16, that's 12, is less than 6 plus x. And subtracting 6 from both sides, we get x is greater than 6. And so in this case, we always will solve this just like an equation. There is one minor difference, which we'll get to in the next problem. We can rewrite this, if you like, as x greater than 6. So we can say 6 is less than x is greater than 6. Those are equivalent statements. I'm going to now represent my solution in a couple different ways. So when x is greater than 6, if I want to represent it on a number line, I would draw my number line. I would draw an open circle around 6 because we're not including 6, and then I would draw an arrow that's heading up because x can be any of the numbers that are greater than 6, any real number greater than 6. I can also write my solution using interval notation. So I can write that this is the same as 6. Notice I use a round bracket. And I put infinity. If I'm just continuing and I'm not going to stop, I use infinity as my right-hand endpoint. Now, if you're taking this course, we all know infinity is not a number, so we don't actually get there. So we don't use a square bracket with infinity. It always gets a round bracket. Because if we were to use a square bracket, that would imply that infinity was a number. And we all know infinity is not a number. So let's look at another example. We've got minus 3 times x minus 5 is greater than or equal to 12. I am going to divide both sides by negative 3. We have x minus 5, but this is my little trick. So when we multiply or divide by a negative, we switch direction of the inequality. Okay. Why? Well, why don't you try it out? Go and take some numbers and multiply them by negative numbers and see if you start with two different numbers. So take like 1 and 2, multiply them by negative 3. Is the number that was greater in the beginning still greater, or is it going to be smaller now? And actually test that out a bit, because that does make sense. All of our algebra rules really just come from what happens with numbers. So now we have x minus 5 is negative 4. And we get x is less than or equal to negative 1. Okay. And we can take that and represent it in interval notation. So we would use, if we're going down and we're not stopping, we're going to use negative infinity. It's not our end point. It's just a representation that we are going to continue going infinitely. And our final example, we have a double inequality. So we're going to restrict our variable expression on both sides. So we have negative 2x plus 8 is going to be greater than or equal to 4, but less than 10. So we're looking for a range of x's that will make this true. Okay, so whenever you see both of this, this is an and, a mathematical and statement, which means that both need to be true. Okay. Whenever you have something that's scrunched between two inequalities, you're looking for things that satisfy both inequalities. So what we can do is we can solve each inequality separately and then look for where the inequalities, those sets of numbers, where those are going to intersect. So we're looking for the intersection of two sets we're going to come up with. So the first set of numbers is the set of numbers where negative 2x plus 8 is greater than or equal to 4. Solving through subtracting both sides, we get negative 4 is less than or equal to negative 2x, and x is going to wind up being less than or equal to 2. Okay, so this is one of my number sets. So this is our set 1. So x has to satisfy the inequality x is less than or equal to 2. On the other side, on the other hand, we have negative 2x plus 8 is less than 10. So we wind up with negative 2x is less than 2, and x needs to be greater than negative 1. So this is our second set of numbers. So we are looking for the set of numbers where x is less than or equal to 2 and also greater than or equal to 1. So what I like to do is I like to actually draw it out on a number line. And I think this gives the most understanding. As you get some practice with these problems, you may be able to just jump straight to an interval notation answer. That's great. So let's look at our first set of numbers. So we have 2, that's one of our points, and we're going to put a point here, and we're looking at all the numbers where x is less than or equal to 2, so we put a full dot here, and I'm going to use a slightly different color. We're going to use yellow and go that way. So the yellow color right here represents all of the numbers that satisfy that inequality that are part of set number 1, and I'm going to use green for my second set, set number 2, and we will just, whoops, that wasn't what I meant to do, set 2, we will put green, and so our set 2 numbers are going to be everything that is greater than or equal to -1. So that is going to come right here and keep going. But we need to make sure we have an open hole around -1. So you guys can hopefully see, and we'll just color that set 1 yellow so that you guys can see set 1 goes with the yellow, set 2 goes with the green. So the area that we're looking for is the place that is both yellow and green, that where we have numbers that are part of both sets, or the intersection. So this is set 1 intersect set 2, and that is this interval here where we have -1, comma 2, and 2 is included in the interval. Thanks, folks. Please check your OneNote for your homework, and I hope that this is useful, and we'll keep on going.